Science and art are often seen as separate worlds, yet at the intersection of nanotechnology and creativity, NanoArt was born. This revolutionary concept transforms scientific discoveries into aesthetic visual expressions, revealing the hidden beauty of nature at the smallest scales. But is NanoArt simply about making research visually appealing, or does it have a deeper purpose? Could it change the way we perceive and communicate science? At the nanoscale, materials behave in strange and unexpected ways. Quantum effects emerge, colors shift due to plasmonic resonance, and structures self-assemble into breathtakingly intricate patterns, all invisible to the naked eye but revealed through electron microscopy, atomic force imaging, and computational simulations. Scientists who study nanomaterials are not just uncovering new knowledge, they are discovering a hidden world of natural design and aesthetics. This realization gave birth to nanoart, where the boundary between scientific imaging and artistic interpretation disappears. One of the earliest pioneers of nanoart, Professor Jeffrey Ozon, recognized that scientific images of nanoscale structures were not only valuable for research, but also stunningly beautiful. Through nanoart, his work, along with that of other leading nanoscientists, showcases the intrinsic elegance of materials where science and art merge into a single language. The field has since expanded, with scientists and artists collaborating to turn scanning electron microscope images, molecular simulations, and atomic-scale photography into vivid visual narratives. What makes nanoart different from conventional scientific visualization? Nanoart does not merely illustrate data, it invites emotional and intellectual engagement with the unseen world of nanoscience. By enhancing colors, adjusting textures, and composing nanoscale landscapes, researchers create images that resemble alien worlds, biological structures, or cosmic nebulae, capturing public imagination while communicating complex scientific principles. But beyond its aesthetic value, does nanoart have practical applications? Can it change how people understand and interact with nanotechnology? Studies suggest that visualizing nanoscale structures in an artistic way enhances public engagement, simplifies scientific communication, and sparks new ideas in research. In education, nanoart can make abstract concepts more tangible for students, helping them grasp the intricate beauty of nanoscience while fostering curiosity. NanoArt also raises profound philosophical questions. Is nature itself the ultimate artist? Are nanoscale structures a form of natural design that predates human creativity? In some sense, scientists working at the nanoscale are not just discovering new materials, they are uncovering patterns and geometries shaped by fundamental laws of physics, much like an artist finds inspiration in nature. As we move deeper into the age of nanotechnology, nanoart may become an essential bridge between scientific research and the broader public. It allows people to experience the wonder of discovery in a way that textbooks and research papers often fail to capture. Could the future of scientific communication rely more on visual storytelling through nanoart? If a picture is worth 1,000 words, perhaps a nanoart image is worth 1,000 scientific papers. NanoArt is an emerging field where scientific imaging techniques reveal the intricate beauty of nanostructures, blurring the line between science and artistic expression. At the nanoscale, materials self-assemble into mesmerizing patterns, creating structures that resemble cosmic landscapes, biological forms, and abstract paintings. High-resolution techniques such as scanning electron microscopy, AFM, capture these formations in unprecedented detail. By adding color enhancements or presenting raw grayscale images, scientists and artists collaborate to showcase the hidden elegance of nature at the atomic level. For example, nanostructured silicon surfaces have been imaged to resemble mountain ranges or ocean waves, illustrating how material properties create stunning visuals. This is like peering through a microscope and discovering an entire alien world made of atoms and molecules. Nanomaterials exhibit self-organization patterns driven by quantum forces, surface tension, and crystallization dynamics. These structures often follow fractals, Fibonacci sequences, or other mathematical symmetries similar to those seen in snowflakes or galaxies. The self-assembled nanostructures can take hexagonal, spiral, or dendritic forms, reflecting the underlying physics governing molecular interaction. This provides a unique perspective on nature's ability to repeat patterns across vastly different scales, from atoms to entire ecosystems. For example, gold nanoparticles can form hexagonal arrays similar to honeycombs, demonstrating how nature optimizes space and energy efficiency even at the quantum level. This is like watching a snowflake form in slow motion, but at a scale a million times smaller. NanoArt relies on cutting-edge imaging technologies such as SEM, AFM, and transmission electron microscopy, TEM, which allow scientists to visualize nanoscale features. Unlike traditional photography, these tools detect interactions between electrons and matter, generating high-resolution grayscale images that highlight the surface morphology of nanostructures. By modifying electron beam intensity and sample coatings, researchers can enhance contrast and capture intricate details that would otherwise be invisible. Some nanoart pieces even integrate false coloring techniques to highlight different materials and compositions, making the invisible world more accessible to the human eye. For example, silica nanospheres have been imaged using SEM to create abstract visuals that resemble surreal planetary landscapes. This is like using an electron microscope as a paintbrush to unveil the hidden architecture of matter. By transforming scientific images into art, NanoArt makes complex concepts in nanoscience more relatable and engaging to the general public. The visualization of nanoscale worlds allows non-scientists to appreciate the elegance of material science without needing deep technical knowledge. Art galleries, museums, and educational institutions increasingly incorporate NanoArt exhibits to spark curiosity about the nanoscale world and its technological implications. This approach fosters interdisciplinary dialogue between scientists, artists, and educators, expanding the impact of nanoscience beyond the laboratory. For example, NanoArt has been displayed in exhibitions worldwide, such as NanoArt 21, where scientific images are turned into thought-provoking artistic compositions. This is like translating scientific equations into a visual language that anyone can understand and admire. Although raw nanoimaging typically produces grayscale images, digital enhancement can be used to apply false coloring for artistic and educational purposes. By assigning different hues to materials, surface textures, and energy densities, scientists can highlight nanoscale features that would otherwise be overlooked. This process not only makes nanoart more visually striking, but also aids in scientific interpretation by differentiating between structural components. However, it is essential that colorization is used responsibly to avoid misrepresenting data or misleading viewers. For example, researchers often colorize carbon nanotubes in blue and metal nanoparticles in red to visually distinguish them in composite materials. This is like coloring X-ray images to help doctors visualize bones and tissues more clearly. Beyond its artistic appeal, nanoart has practical implications for materials science, influencing the development of new materials with engineered optical, mechanical, and electronic properties. By studying the aesthetic formations of nanostructures, researchers can identify underlying growth mechanisms, defects, and novel fabrication techniques. Some companies even use nanopatterning techniques inspired by nanoart to create advanced coatings, bio-inspired materials, and next-generation electronics. The intersection of artistic visualization and material engineering opens new doors for creative scientific discoveries. For example, self-assembled nanoscale photonic crystals, which create iridescent colors similar to butterfly wings, have inspired next-generation anti-counterfeiting technologies. This is like using nature's patterns to design futuristic materials that outperform human-made technologies. Fractals, which are self-repeating patterns found in nature, often emerge spontaneously at the nanoscale due to molecular interactions. These patterns can be seen in crystallization processes, polymer growth, and dendritic nanostructures. The natural occurrence of fractals in nanomaterials suggests that some universal mathematical principles govern both biological and non-biological systems. Studying these nanofractals helps scientists understand how complex systems organize themselves at microscopic scales. For example, nanostructured graphene flakes often self-assemble into fractal-like formations, resembling snowflakes or river networks. This is like seeing the same pattern in a tree's branches, a coastline, and a microscopic crystal, all following nature's blueprint. As imaging technologies evolve, nanoart will become even more intricate, revealing previously unseen details of nanostructures. The integration of artificial intelligence, AI, and machine learning will enhance the ability to process and interpret nanoscale images, generating real-time artistic representations of atomic landscapes. In the future, holographic projections and augmented reality, RI, may allow audiences to experience nanoworlds in immersive 3D environments. This progression will make nanoart not just a visualization tool, but a powerful medium for scientific discovery and interactive education. For example, some researchers are exploring AI-generated nanoart, where algorithms enhance nanostructure images to reveal hidden patterns and structures. This is like giving a microscope the power to paint a living, evolving canvas of nanomaterials. Nanoart is not just about aesthetics. It represents a paradigm shift in how science is communicated, understood, and appreciated. By visualizing the beauty of quantum mechanics, molecular interactions, and self-assembly, nanoart provides a tangible way for society to connect with the microscopic world. This artistic, scientific synergy inspires the next generation of scientists and fuels innovation by merging creativity with research. As science progresses, nanoart will continue to be a bridge between the complexities of nanotechnology and the curiosity of human imagination. For example, nanoart has been used in STEM education programs to inspire students by showing them the unseen beauty of scientific research. This is like turning science into poetry, where every microscopic image tells a story of the universe's hidden wonders.